We've looked at the real eigenvalues so far, and now we have to look at the complex eigenvalues. We have also looked at the graph of how a complex eigenvalue looks. Now let's just do a problem and see how the solution is going to look and why is the graph being spiral or concentric. Okay, this is an example problem, so we're going to go through it and let's see what happens over here. Okay, so solving is going to be very similar to the previous ones, so I'm still going to start off with a minus lambda I is equal to 0. So when I do that, I'll be getting minus half minus lambda 1 minus 1 and then minus half minus lambda, and the determinant is equal to 0. So I would let you to go through the calculation for the determinant, and I'm just giving you how the equation looks like. So you would get lambda squared plus lambda plus 5 over 4 is equal to 0. And again, if you go through a few steps, and then you'll be able to find that your first eigenvalue is going to be minus half plus I, and your second eigenvalue is going to be minus half minus I. Okay, this is actually a checkpoint for these kind of questions. So it's very important to get your eigenvalues in the form of mu plus or minus IV. So if one of your eigenvalue is mu plus IV, then the other eigenvalue must have to be mu minus IV. There cannot be any other exceptions there. So when you're finding the answer, you can just make sure if you get it of this form, and if you're not getting that form, you know it's going to be wrong. Okay, now we proceed to finding the eigenvectors. So we're going to do a minus lambda 1 I times v1 is going to be a 0 0. Okay, my vector a minus lambda 1 I would become minus half minus of minus half, and then minus I, that would just make it minus I. That would be 1 minus 1, and this one's again minus half minus of minus half minus I, so it'll be minus I times v1 is going to be 0 0. Here we can find v1. So look at it. Let's say I'm taking 1 time of my first column and then I times of my second column. That would give me 0, right? Because even over here, because negative I times minus I squared is actually positive 1, so it works. So it's going to be 1 and I. That's my first eigenvector. And I'm actually giving you the next eigenvector without even solving it. And I would say that the second eigenvector would just be 1 and negative I. Okay, it's better if you go through the calculation for a minus lambda 2 I into v2, but you will end up in this form because over here we had mu plus or minus IV, right? So whenever whenever complex eigenvalue comes, we always get it in pairs. Similarly with even eigenvectors, the complex number I always comes in pairs. It's always plus or minus I. Okay, if you're again not getting 1 and negative I, then your answer is going to be wrong. This can be your second checkpoint if you're doing things correctly. Now we have both our eigenvalues and eigenvectors. Now we can go about forming our solution. If I'm going to take the first one, so my x1 of t would be e raised to the power minus half minus I, right? Or sorry, it's plus I, times t times the corresponding eigenvector. So that is going to be my first x. Similarly, I can do for my second x also. My x2 of t would be e raised to the power minus half minus I t times 1 and negative I. Okay. So once I have this, I can do a linear combination and get my answer. But just in the previous step, we have seen that the complex numbers always comes in pairs, right? You can see the similarity between these two functions. What I am telling you is, let's just take one term, okay, and we'll split this into its real component and complex component, and hence we'll still have a linear combination of two terms there. And we can henceforth tell that that is a final answer, or that is a solution to this differential equation. Let's see that in the next video.